Lo sí que lo tendrá. Entonces,
No me puedo descolocar a mí mismo.
entonces, a eso hay que fijarnos y una vez
Como é que é?
Hello, everybody.
Hi.
Good afternoon, sorry, and welcome to the second online show of Team Design of IBEC Final 2021. Today, our participants will be presenting the outcomes of the work they have been doing during the past 2 days. We will see their approach to solving a practical problem by means of building a prototype. The order of today's presentation would be Owau, Mochienie Nyakliapiev, Ale Hakotak, I'm sorry if I pronounced it bad, Grololoch, Wannabe Engineers, Mission, We've Eaten, Engineers, Solid Dome Works, Spigoli Vivi, and Visichanari. The order will be this one, and the time you will have to present is 8 minutes. After 8 minutes, you will be penalized, and after 9 minutes, you will be cut. Then we will have another 8 minutes for the jury to ask any questions they might find relevant. Therefore, let's start this team design show. Oh well, the stage is yours.
Hello. Okay. Hello, everyone. We are Team OO, and we present you our product, the Glow-Wows. So Marie will start with the description, then Didert will explain our concept, Polly will clarify all the materials that are used, and then in the end, I will give a recap with all the highlights of our concept. Now I give the word to Marie.
We had to make a rubber glove with all these characteristics. It is a glove for an adult arm and it has reached the elbow. It is to be as light as possible and the normal movement of the hand must not be destructive. When you are not wearing the glove, it has to be compact. Further, it must be fire resistant, shock damping, impact resistant, and heat resistant. It also has to made from easy available materials.
In order to make this glove as compact as possible when folded in, we chose a two-part design. The hand itself consists of a few layers to deal with heat, fire, and impact, which will all be explained in a minute. The arm is a strong structure that functions as a compact, retractable storage space. The design will allow us to make the hand flexible and fully articulate, but also provide excellent protection due to these layers I mentioned and the black knobs on top of the hand, which will distribute the load of an impact to a larger area. All of this whilst the arm remains completely guarded from heavy impacts and heat sources. When not needed, the arm structure retracts in a telescopic manner. This makes it a compact cylinder in which a sleeve and a hand can be stuffed. Since you have two hands, the retracted cylinders can be attached to each other with leather straps.
Now I will describe all the materials. I will start with the hand part of the globe, and I will describe the structure layer by layer. And I will start with the first layer, the one that is closest to the skin. The first layer is a sport compressive glove and sleeve. It is elastic, breathable. It absorbs your sweat and it absorbs shocks, what makes it very comfortable. And it's a perfect first layer for our Glow-Wow. The next layer is Nomex. Nomex is especially known for his good properties against fire and heat. It's almost used in every suit of fireman or firewoman, and so it's very known for that. It's also durable, flexible, and resistant to chemicals, and also lightweight. The next layer is Kevlar. I think everyone knows Kevlar. It's a very good material. It's resistant to cuts and not also like Nomex, fire resistant, chemical resistant, and flexible. And that's the top layer of our glove. The next layer is different for the top and the palm. The top has to provide impact resistance against high impact, and we use ABS for that. It's a strong plastic, and as you see on the image, the ABS is in little black dots just above the knuckles and the joints to protect them. And because it's only there, you can still move your hands naturally, and it will not disturb any movement. ABS is also chemical resistant, and it performs excellent in high and low temperatures. It's also easy to manufacture, so it's a nice material to protect the knuckles and the joints against high impacts. The palm of the hand will provide a damping absorbs vibrations. So the material has a superior damping coefficient, and it's also resistant to fire and chemical solvents. The material we use for that is sorbitane. It's a rubber, and so like I said, it absorbs vibration, and it has a superior damping coefficient. It's also durable. And the sorbitane layers are placed in strokes on the hand, and between the strokes there is air, so you can still move your hand like this, and it will not, no material will be in the way for your hands. So yeah, we use that material for the palm, and then we're ready to go to the next part of the glove, the sleeve, and I will give the word to Anka.
Okay, so the structure of the sleeve consists of two layers. The first layer is the sport compression sleeve, as Polly already mentioned. It's the comfortable on the skin. And then on top of that, there is a hard layer of composite. We wanted to have a lightweight material that was impact resistant and fire resistant. So that's why we chose the composite Duplicor. And an additional advantage is the price and the ecological aspect. Now, a recap of our concept. So our product meets the task requirements like being compact and heat and fire resistant, but it also has these extra advantages like being cut resistant, breathable, sweat absorbing. So that was our concept. These are our sources that we used, and that was the end of the presentation. Thanks for your attention, and now we're ready for the questions.
Okay, who is first for asking? It's me, maybe?
As you want, no, yeah.
Okay. Well, first of all, congratulations for presentation. You have been designed a very nice glove, and I think it could be a possible solution for, I didn't understood what kind of people who would be the users of this glove. Just protection against heats or against fire. That's all. And about fire, I disagree about Kevlar in fire protection, because Kevlar maximum temperature could be working with a safe way is 315 degrees. So maybe there are other options, and the mix between Kevlar and carbon fibers, this could be a nice option, but the mix, not just Kevlar, but it's just for you for knowing. And my question is, this glove is not interacting with the neuronal parts of the arm, isn't it?
Could you repeat your question?
Yeah, the question is, this glove is just a protection glove, an external protection glove, or it's interacting with the arm, with the properties of the body, temperature, pump, blood pump?
No, it's not such a smart glove. It's just to protect you against heat and
Okay.
fire. And about that Kevlar thing, I think Kevlar is a knitted in our glove, and in a like if you knit a material, you can almost add some other fibers that make it extra fire resistant. So that we can add to the Kevlar to make it more fire resistant, and I'll have the cut resistance also in combination.
Okay, great. And maybe you know it, Kevlar was invented by a woman, Stephanie Kwolek. She was the inventor of Kevlar, the best invention ever. That's all. Thank you very much.
Thank you.
Okay, so maybe let me ask my question. So first of all, I would like to congratulate you for the presentation for the design. I think this is quite nice, and I totally agree with Noria. So most of the questions I was going to ask, so Noria take advantage, right? So regarding the fire protection, I had a very similar question, and this is related to the, so basically your layer thought because of that is somehow in an intermediate region, right?
Sorry, I didn't understand well.
You have different layers.
Yes.
Your layer that this is supposed to be fire resistant is somehow in the middle of the whole thing, right?
Yes, but that's normally the thickest layer. So the layers above, like the Kevlar, would be just a small layer, I think 1 or 2 millimeters. So the Nomex is really important because it's the thickest layer.
Okay.
As an insulator then.
Yes.
Okay. And what about the let's say the connection between the different layers? So I don't know if you have mentioned something about the joints or adhesive layers or something like that.
No, we thought maybe a kind of glue or something that presses the layers together. Yeah, and like the suits or of firemen I mentioned, it's also Nomex, and then a thin layer of something else. We could use the same glue for our glove.
Okay, because I think this is quite important actually, how you join the different layers.
Yes.
Well, so also just last question, because I'm going to spend the whole time there. How did you choose the different thicknesses or different layers? So what was the motivation? So just looking into the literature, or?
We especially based this on other gloves and other things with Kevlar in and other materials we used, and then we took the measurements from that. And yes, it's always a little bit thinking and not be sure, because if you want to be sure about things, you have to test it. And yeah, we couldn't test it a bit, yeah.
Okay, I think I'm going to stop here. Just to...
Okay.
Congrats again.
Thank you.
Thanks.
Now it's my turn. I would like to ask you a couple of questions about the weight and the heat isolation. Did you estimate the total weight of your concept?
No, but we looked for materials who are lightweight, and we took a look to other gloves with some same materials, and they were also not heavy or something, and good in use. Like if you read the reviews, it was kind of okay if you think about weight.
Okay, and also another couple of doubts I have is One thing is related to the, did you consider the thermal comfort of the person? So, because at the end, how many hours should be possible to wear this without feeling uncomfortable for the user?
Well, the layer of the sports sleeve should make it really comfortable. It should wick your sweat away from your body, which will keep you cool. It's also used for athletes who sweat a lot and become really hot. So we think it should be fine to use for a long period.
And I think also if there is such a hot source, then I think your face and other parts of your body will have more heat problems than the arm and the glove.
And last question, you used the ABS for the protection of the, let's say, of the junctions in the hand. Why didn't you think about using these non-Newtonian fluids, which are more totally flexible but are resistant to high-speed impacts?
Fluids.
Did you mean fluids instead of the
Yes,
plastic?
yes. You could have used some non-Newtonian fluids. So you have fluids which are behave like a fluid if they have a slow deformation, but if they have a very fast deformation, they behave as a solid. So this could have been this could have allowed you to protect the entire hand everywhere.
We have thought about that, but then our struggle was how do you make it compact, and we didn't, or we thought that this, so the ABS in combination with this textile could be more compact when you want to fold it. And if you have this fluid, then you have to maybe pour it into something when you want to fold your glove. So that's why.
And on top of that, this non-Newtonian fluid has a lot of resistance. If you try to move it, it takes quite a lot of force to move the fluid out of your way. So in our design, it gives a lot more flexibility to move your hand.
Okay, thank you very much.
Thank you.
Thank you.
I think we are out of time and we should go to the next one, right?
Yeah.
Yeah.
Okay.
Thank you.
Thank you.
Bye.
Thank you. Thank you, Timo Wow, for your glow design. Now it's time to move on to the next team. So Mochinie Nieklapie Kale Hakotak, or sorry, it's your turn. You can show us your designs.
Yeah, let's set it up. Can you hear us?
Yes.
All right. We are Może nie najlepiej, ale jako tako, and we would like to present our solution to the task, the protective glove. We had some inspiration. They were connected with both the heat and shock resistance requirements. We checked what materials they are, what they are made of, and what is their internal structure. This is the general structure of our glove. The whole glove is made from multi-layered composites, and most of it contains inflatable middle layer. The surface of the hand is knurled to increase grip. There are several electronic components inside, namely an electronic air pump, valves. There are in the pump and the valves are inside the forearm. There is an air temperature sensor on the palm of the hand, and an IR sensor, a display, and a battery tray located on the top of the forearm. The main feature of our solution is an active thickness control system. It allows for dynamic adjustment of pressure inside the middle layer, allowing for both good insulation and impact resistance without lowering the dexterity if it is needed. It also requires less space in transport or storage. The air jackets inside the middle layer are separated into two. This means that during gripping, the protection of the entire hand does not need to be compromised. There is a polyamide ribbing inside the middle layer. It is impact resistant and ductile and conforming to the arm's shape. There is a possibility to 3D print the ribs, so they will fit perfectly over the operator's arm. The glove is equipped with multiple sensors. The inside and outside temperatures can be recorded. The pulse and oxygen saturation of the operator can be also measured. We have used several materials. They were chosen because they are non-flammable, heat resistant, and insulating. They are also non-toxic, soft and flexible, and will provide both tear-proofness and chemical resistance. The outer layer is made from aluminized para-aramide with fiberglass. It is a wove of Kevlar and fiberglass that is coated with a thin layer of aluminum, and its main purpose is to reflect heat radiation. The middle layer is made mainly from rock wool. It's the main insulator of the composite. It is very compressible, and the feature is used for active thickness control. Another material used in the middle layer is silicone. It is used to create airtight tubes around the rock wool and most of the pressuring system. The next material is PBI, that is highly resistant to fire and chemicals. It is used in firefighter and astronaut suits. Another material used in the middle layer is polyamide. It is used in small strips to grant impact protection. While being strong, it does not break, and it can be bent. The wool and polyester knit is used on the very inside of the glove. It is very nice to touch, breathable, and naturally prevents odor. So this is the cross-section of the multi-layer composite we prepared. As we said before, the outside layer is made from aluminized para-aramide used in metallurgical gloves. The middle layer consists of silicone chambers filled with rock wool, and the inside layer is made from PBI. The silicone walls create the chambers and make sure the wool is evenly compressed. The polyamide ribbing is placed together with rock wool inside the middle layer. The material on the inside is soft here, comfortable, and prevents excessive sweating. Grooving in the polyester wool composite helps with air circulation. The electronics technology used is commonly found in consumer electronics. The air pump can be made from coils and a silicone bubble, making the whole system flexible and able to be rolled up. And in a case of electronics failure, the glove can be hand pressurized. We have designed the glove with regard to the presented requirements. Every requirement was considered when the design was created. When it comes to size, the air chambers are resizable depending on the demand. The only rigid parts are placed in horizontal strips. And together that means that the glove can be easily rolled up. Regarding the materials, the ones used are tested and proven to work in extreme conditions. While they are specialized, they are produced in big quantities and can be easily obtained. Concerning the weight, thanks to thoroughly chosen materials and design, the gloves are lightweight. The rock wool filled air jacket that is used as the main insulator does not increase the weight of the product. And the total weight sums up to below 450 grams. That is around 25% of the weight of a human arm and will not be tiring to wear. While the materials and technology used in glove production are well developed, they are also fire resistant. As we said before, there are sensors placed on the back of the hand and the electronics case. They can measure the heat of the environment and notice you in case of danger. Concerning the shock absorption, the vibrations are dampened by the air jacket and other soft layers significantly. There are no hard materials directly in contact with the operator's hand. When it comes to impact resistance, the air jacket combined with the polyamide ribbing absorbs the impact and spreads over greater area. And that's all from us. Thank you. And here's the bibliography.
Well, I suppose it's my turn for questions. First of all, congratulations. You have shown a very, very nice and possible design of globe, maybe quite heavy, I think. 400 grams is, I think is too much. Maybe not the first 5 minutes, but then it would be too much. It's my consideration. And what about the impact resistance? What about the toughness, not toughness, resilience of this glove? What about mechanic resistance in front of the heat?
Well, we thought that when we have a metal shield or something like this, the energy of the impact still comes to the hand. So if we can spread the heat with the air pressure and the ribbing, it will be basically the same. So you still are not the pressure is not exerted on the small area on the hand, but maybe goes more around it.
Oh, and in the case that a big heavy piece falls over the hand, maybe this metallic structure could hurt the arm or not?
Well, it depends. When it's really heavy, it can.
I know it's a very bad question. Yeah, I know.
It also depends on the load, because it can maybe collapse, and this is more like a cushion. So when something heavy hits, maybe it's more bounces back instead of stopping on the.
This is always the discussion about safety gloves with metal or without. Because metal is, of course, the best protection, but in front of a big, a heavy piece on top of the hand, the metal could be your worst friend. But that's okay. That's all. Congratulations again. Thank you very much for explanation.
Okay, so congratulations. So to be honest, I really like some of the ideas that you put inside the design. And actually, I'm surprised about some stuff you presented. And my questions are more related to the feasibility of the design. So something I don't really understand is how can you adjust the thickness of the whole glove? So which is exactly the system. So I understood that this is by kind of air pumping, but how big is the system you need and where this is placed into the...
Let's say here on the presentation. So the pump is in here, and basically the whole structure is made of, maybe you have a photo here. It's like tubes of wool, and inside is a rock wool. So it's a very soft material, and it can be compressed like 10 times. So when there is the pump can work both ways. So when it is vacuumed, the wool is very compressed, and it's like a tight glove. But when the chambers are pumped full of air, and then the wool expands with them, and the outside material can be it's not that that hard that it can't fold a bit. So it's not it can let's say with the air inside it takes the bigger shape.
I see. So here's what I wanted to come. So related to the Nuria's question, about the impact resistance. Okay, I agree with you that once you have air, you have some dissipation of the mechanical waves, etc., etc. But my question is, as soon as you are impacting that, how good has to be your pumping system to trap the air?
Well,
Could be the case that just when you are impacting, so all your air is going through the whole thing, right? So you are losing the whole protective.
Well, it depends, because if we have a valve system, the whole chamber can be, let's say, pressurized and then disconnected from the pump. So then it is acting like a closed chamber. And when, for example, it is folded up, it can be turned, the valve can be turned on, and then it can be, let's say, an open chamber. So it's not pumping the whole time. It's just changing the pressure depending on the demand.
And the system is perfectly closed, right?
Yes,
so you don't have considered that maybe you have a given pressure that you break the system, or
well, in case of damage of the pressure system, well, there are still the rest of the layers that should be enough of protection.
Okay, so thank you very much and congratulations again. So really nice design, really.
Thank you.
Thank you very much and congratulations. I think that the design is very nice, and also I really appreciated your quantitative estimations that you are providing. I agree with Daniel and Nuria that the glove is a bit heavy, and I'm a bit I'm a bit worried about the capability of moving the hands, the fingers. So imagine that you require to hold something and so on. I'm not sure whether the user will be able to apply this force. Can you discuss a bit more this?
So let's say normally the whole hand is pressurized and you can't really move the fingers that much, but when, let's say, just the inside surface of the hand is vacuumed, then it should be about 3 milliliters thick. So I don't think it's that thick to not be able to hold anything. And also because there is a difference in pressure, it should be like the pressure should it's also exert some force, grabbing force, so it can help you hold on to things when the inside is depressurized and the outside is pressurized.
Okay, and then I have also another question. I wanted to hear from you if you thought about the operating life of this object. I mean, in the previous presentation, we had an object which was much simpler, requiring less moving parts, requiring less sensors. So here there are a lot of things that can break. And did you think about what will be the reliability of this object?
Well, while the cost was not a given problem in the task.
Yeah, I know. I'm asking.
Yeah, but we thought that, for example, the PBI is on the very inside. It probably should be higher, maybe outside of the air chamber, but we thought that the most protective layer should be on the inside. So even if in case of failure, so like the aluminum is stripped, then the Kevlar can be burned, then the silicone can melt. So the most protective layer, the PBI, is on the inside, and even if high temperature is around, it should be enough to protect the user. So yeah, and like we said, the electronics are not needed. So if the valves can be also operated manually, the pump can be probably also operated manually.
Okay, thank you very much.
Thank you.
It's all for me. Thank you.
Thank you for your solutions. It was a very interesting device to see. Now we can move to the third presentation of Team Grolaloch. You can share with us your results.
Thank you very much. So I will wait for my teammate to share the presentation, and we shall begin.
Yeah, I'm working on it. Yeah, so you should be able to see my screen, right?
Okay.
Okay.
So hello everyone. We are Team Krolog from Brno, and we'll present you our solution. I'm Filip, Team Tech Captain. Hi. Next to me is Kubo.
Hello, I'm Kubo.
And also in our team there is Lucas and Dominic.
Hi.
Moving on. When we started researching for our glove, we took inspiration in many things, like the ordinary stuff gloves you probably everyone have at home, and also it had to withstand forces like impact forces and vibration. So we took inspiration in armadillo, the small mammal, and also in knight armor. Next slide, please.
So when it comes to materials we used, for the main armor part, we used carbon fiber for the frame. We also used PBI fiber, the polybenzimidazole, for the heat resisting parts, and for the insides of the carbon fiber frame, we used memory foam for comfort and vibration absorption. And we covered the entire glove in /pro protection for protection from knives and sharp impacts. Here you can see the glove, sort of half disassembled. It is built out of three main parts. The hand covering glove, which is built almost entirely of fabric with armored inserts, which is then connected to the forearm impact cover, which helps against heavy impacts and sharp impacts. The inside of it is covered in memory foam, and then the heat protective sleeve, which is then pulled over this impact cover. Here you can see the layers of the fabric used for the glove and the heat protection sleeve. Here you can see the glove when the heat protection sleeve is pulled over it, and the insides of the impact protection sleeve. Also the memory foam inside of it.
We also put armor insert into the glove, which helps to protect upper part of the hand. Next slide. As you can see, there is open forearm cover where you put your hand and pat on glove and then close it, and finally slide on the sleeve.
As you saw on the last slide, the whole fabric part can be folded inside the rigid part of the glove, as seen on the video on the right, below right down. So next slide, please. We designed our glove to fit my hand, which is quite big, but we, in case of bigger manufacturing, we would provide them in standard sizes of the gloves, so from 8, 9, and so on. So we will use the standard size for the gloves.
We use classic water cooling circuit with external cooler, coolant tank with pump for circulation of coolant, and cooling is necessary for better heat resistance and more user comfort. Next slide, please.
It is also, of course, optional because the equipment required for this is quite heavy, and it's better if you want to be lightweight to remove this.
Yes, so the whole glove is equipped with the points to attach the hoses, and the whole cooling mechanism would be on your back in some sort of backpack.
And we also designed a heavy-duty version of our glove. With this is more armored and provided better protection and endurance. Of the other side is limited finger movement. It can be used for special application with extra hazard of injury.
So that's all from us, and we will be glad to answer your questions.
Well, boys, thank you very much for your presentation. And sorry, excuse me, I didn't realize to have learned about the weight of the element.
Well, we considered to use the most lightweight elements, but for example, the fireman gloves, which we based heavily our design on, weighed approximately 300 grams, or I'm not sure.
You can say it in pounds. No,
well, in pounds.
We use the metric system.
The metric, perfect for me. It's perfect. I'm from Spain, so metric is perfect for me.
We're all from Europe, so most of us.
How many grams?
Well, the fireman gloves weighed approximately 200 grams. So
200, and all the glove?
No, there's extra weight, some extra weight in
there would be some extra weight, but we didn't want to compromise the protection, so it's more like an armored glove than a working glove. But there was
but the weight is one of the items you must consider in the rubric. So is a data we need to note for assessment. And when by in addition, the armor, the fire protection, and the extra protection metallic, like Wolverine structure.
Just one thing: the protection woven in is not necessarily metal. Just like the armored sleeve, it could be made of carbon fiber, for example,
or
which is very lightweight.
Carbon fiber. So
or some other composite.
We're talking about 1 pound, 400
about 400 grams,
more
I would
or
say,
less.
Yeah.
Okay. Well, then it's the same that the previous team. I think is heavy.
Yeah.
It's heavy. It could be good for protection, but heavy. Okay, that's all. Thank you very much, boys. And maybe if you consider to add a girl to your team, and then maybe these aspects could be considered about the heavy, the weight. I'm kidding you. No worries.
We would have had a girl if one was available. But...
I'm kidding you. Okay,
no,
that's
no.
all.
Okay, thank you.
Thank you.
So congratulations again for the presentation and the design. So my main question is related to the impact resistance. So please correct me if I understood something wrong, but to me it's like you paid a lot of attention about this region of the arm, but probably the glove is not that good protected, right?
It is a little weaker, of course. It has to be weaker if you don't want to sacrifice a lot of movement.
Okay, but so that's my point. How resistant to impacts do you think your protective device is for the hand itself? Because to me it looked like quite soft, right? So quite compliance.
Well, compared to standard heavy-duty gloves, it's, I think, even more impact resistant because of the inserts. But of course, you have to sacrifice some resistance for mobility. If you're talking about a work glove, you have to also be able to work in it.
Yeah, if you put your hand inside a steel or composite tube, it would be best protection you could achieve, but then you will have limited movement. And well, you can use some sort of claw or something, but you still have to work with it. So
It's still supposed to be a glove, yeah.
Okay.
Yes, it was.
Okay, so well, that was my main concern, let's say. So congratulations again, and that's all for me.
Well, congratulations. I think you've done a nice job. And I would like I would like to ask you, how would this be produced and manufactured in terms of feasibility?
Yeah. Could you say that again, the last part? I think I misunderstood you.
In terms of feasibility of your object, how would you manufacture it?
Yeah, so well, the carbon fiber is quite easy to shape like into simple shape like that. You can of course mold it.
Well, the /Pro fabric is right now can be manufactured to the desired shape. It's a special fabric which is resistant to cuts, and it's manufactured only by one firm, one
company.
Company, yeah. But it's still shapeable into glove-like pattern, and
even if the inserts were metal, they could be pretty easily laser cut and used like that. But we decided to use carbon fiber. Pretty much everything is made out of fabric that isn't easily moldable. So
thank you.
Thank you.
Yeah, and also in terms of heat isolation,
yeah.
Do you think that there is some margin of improvement?
We could use a stronger heat protection. We wanted to protect the heat protective layers from damage, for example, by cutting or sharp impact or impact, because of course, if you were to damage that, you would be in great danger from heat, which is quite important. So we wanted to hide the heat protective layers. But if we wanted to really improve on that, we could use less protective layers on the top of that and simply make it stronger, or find some other cooling materials that would protect it better. We could use ceramics, of course. That would be a way to improve it.
Okay,
maybe
thank you very much. Thank you very much. I think we can go forward. Thank you.
Thank you very much.
Thanks.
Very much.
Thank you, Team Grolov. Now it's time to proceed with the following presentation of Team Wannabe Engineers. The floor is yours.
Okay, hello. So I assume you can hear us. So yeah, let's begin. Okay, we're the Wannabe Engineers, and this is our enhanced kitchen globe. So you all know the task, so we'll skip it. Now, the dimensions, the measurements were made based on my hand, but you can easily scale it up or down for other hands. Now, the globe consists of a soft composite material on the bottom, and on the upper part of the hand, there's a titanium exoskeleton for impact resistance. Now, the thickness of the soft globe is 3 millimeters, and 1.5 millimeters the exoskeleton, and at the hand both are thinner. Now, the estimated weight is not actually 700 grams, as you can see there. That was a mistake, and it's approximately 500. Now, the composition of the soft globe. The base layer is neoprene, which is for shock absorption and for comfort. The other layer is 2 layers of Kevlar, which has a very high tensile strength, and it's also great at it has low thermal conductivity. On top of all that, there's a silicon coating spray, which can stand high temperatures, is flame retardant, and if it's damaged, it can reapply it. Now, in the hand, we skip the neoprene layer to make it thinner and more agile. On the thumb, it's embroidered with conductive thread, which allows the use of touch screens. all the materials we've used so far can be easily found on common marketplaces.
So this is the metal exoskeleton, which, as we said, protects from hard impacts. The floating finger joints are attached to the fabric with Kevlar stitches, and the box on the back, sorry.
Okay.
What's happening? I have a problem with the presentation, sorry.
Okay.
And the box on the back is a surprise for later. The forearm armor is made of 1.5 millimeter thick light titanium sheet and is designed to fold towards the arm, the hand, like that, as you can see in the video. But how does it all fold? The fingers fold in the bottom of the palm, and the forearm fabric is attached in the back of the exoskeleton so that it folds like bellows as it retracts. It grabs it along with it. On the left is a bottom view, and in the right is a front view.
So we could have ended it here, but instead we decided to get creative and a bit childish. So we now present our spiced up kitchen glove. All the electrical gadgets you'll see are powered by 3 lithium-ion batteries, which can be recharged with the USB Type-C. On the battery pack, which is under the box Jerry mentioned, there's a master switch, which powers all of the circuits and allows the use of the gadgets. All the cable work runs between the 2 Kevlar layers. Now here's an overview of their circuits. I won't go into detail, but you can look into it later.
So how all the gadgets work with the gestures. So how do we detect when a finger is closed? Well, there's a metal plate on the end of each finger, almost each finger, and a metal plate in the palm. So when you close that finger, they make contact, the logic board, and the logic board gets that signal. And on the right, you can see our logic board because we're electrical engineers. You can look into it later. First gadget, taser. I know it's a bit stupid, but anyway, it's placed on the 2 poles are placed on the middle and ring finger, and they activate with this gesture. That means you have to keep your index and pinky closed while the other 2 are open. This is the circuitry. You can look into it more afterwards. We also have a laser on the index finger because that's the finger with which you point, and it activates when all other fingers are closed. Also, we do have a lighter. It's positioned on the thumb, and it activates with the thumbs up gesture. Well, it's an electric lighter, so it produces spark, and then our LPG tank, liquid propane gas, provides enough gas to keep the flame going for as long as you keep this gesture. We also have a non-electric gadget, a screwdriver, because we are engineers. And it's positioned on the pinky finger. And it's also detachable, so you can change heads. Finally, we copied Iron Man. We put a flashlight, a thin cylindrical container that contains LEDs, and it has a power of 10 watt, and it activates when all fingers are open, and of course the main switch should be on too. These are some of our sources. Thank you. We're the Wannabe Engineers, and any questions?
Yes, definitely. I have some questions.
Okay.
700 grams is too heavy, but after seeing all the gadgets, I can understand that the reason of this heavy element. This is really a gadget glove for a movie, for a horror movie, maybe. Okay, I'm kidding you. Well, I'm trying to repeat all the movements as well as you were showing the glove, and for the taser, for me it's very difficult to put these fingers in this place when these others are you know.
Yes,
so
yes.
That's an information.
Yeah.
And why titanium? My question is, why titanium? Titanium is heavy. For this for this application, titanium is too heavy. Why titanium?
Okay, so we have 3 questions. First of all, not 2 questions actually. First of all, 700 grams is what we wrote in the presentation. We realized we made a mistake in our calculations, and it's about 500. Now, titanium.
500 is too heavy still.
Yeah, it's still too heavy for some. Okay.
We wanted to use metal because when it takes an impact, it dissipates it in the whole surface, so it hurts less. and titanium was the lightest option we had.
I don't think so.
That it's twice as dense.
I disagree with you that aluminium could be the same option for dissipation energy at this level.
Yeah,
and
but we made
the,
it. We think we made it very thin, so aluminum would be too soft. It would deform immediately.
So, and about the taser, well, yes, this gesture is a bit awkward to hold, but this helps also with safety. We could put it in other gestures like this one, but because this is difficult to use, it's also a safety feature. You can't activate the taser by fault.
well, okay, it would be difficult for me to use the taser, but okay.
Yeah, sure, but you probably wouldn't have to use it so many times.
Okay, thank you very much. But the glasses boy, what's your name?
I'm Eugene.
No, not you, the other glasses boy.
I'm
okay. About aluminium. Aluminium is soft when it's pure aluminium, but aluminium, alloyed aluminium could be resistant and could be hard and could be, as well as some titaniums. That's my opinion as materials teacher. That's all. Okay, thank you. Thank you very much.
Could I add something about the choice of titanium?
Oh, she's a team member.
Hello?
A girl, and the girl is hidden. Oh my God.
She's separate. She's not in the same room, unfortunately.
Oh, yeah.
Yes. We searched about the mechanical properties of aluminum and titanium, and aluminum is it reaches half the tensile strength of titanium in the maximum.
I know, yes. But the level of stress you are going to reach with this element is not too much, and is
yes,
enough for aluminium.
It could be replaced.
That was my intention for explaining. That was
yes.
Of course, in absolute values, titanium is much better than aluminium, but it all depends on the maximum tensile stress or the maximum stress you are going to apply to this element. And the maximum value, it would be not too much, because if you apply a very high stress, the hand is crushed. So it doesn't matter what metal. Yeah. That was all.
Anyway,
Thank you, Jenny, for explanation.
If I can help them, perhaps we can consider that when you go at high temperature, aluminum has a high thermal expansion with respect to titanium.
Yep.
And maybe for this reason, it would allow you not losing the mobility. But I'm not sure. I'm not an expert in materials.
You're right, but the explanation would be the same. If the temperature is too high, then it doesn't matter, because the hand is burned. So no worries for this.
Yeah. Anyway, no way. Aircrafts are made on aluminium. So the material which maximizes the structural response for a certain weight is aluminum is better than titanium.
Yeah, actually have worked on impact response of different plates for very high impact. And actually we consider aluminum and titanium. And to be honest, I agree with Nuria that probably regarding just the stiffness, tensile strength, etc., with titanium you are more than okay for this reason. Not sure, maybe regarding because you have a kind of flame, right? For one of the, by the way, I can do it.
Nice.
Okay. So regarding this, I was wondering about the fire resistance of all the surrounding elements there.
Okay. You mean the fire resistance of our gadgets?
Yeah, so all the surrounding tissues.
Well, okay, so about the laser, there are industrial lasers even used in nuclear reactors. So we're sure we can find one that would be completely fire resistant. Also, but the taser posts, they're just metal, so and the screwdriver
and the LED.
and so we would find also some metal that would be fire resistant enough. And
Also, the only problem that's left then is the cable work, so that
the
insulation doesn't melt. So that can be made with fiberglass, which is quite fire resistant. Also, most of the cable work runs between the two layers of Kevlar, so it's only the exposed cables that are the problem, which are just tiny bits.
Okay, so just would like to know, being super honest, how feasible you think this is to incorporate all these gadgets with all these different features? Because to me, I mean, I'm not expert on that, but
yeah, okay. So of course the gadgets are optional. Our initial design was the previous one we showed, and okay, we're sure they're not that resistant as a glove itself. So the glove itself, we think it is feasible. Look, so all the materials we used, we could find them on the internet. These are screenshots from Amazon and eBay, literally. And the titanium, okay, Jerry, or Eugene?
It's and the titanium is just titanium sheet, which is cut or bent into shape, and sometimes it needs welding. So this far, it's fairly feasible, we believe.
Now, putting all the cable work between the two Kevlar layers would be somewhat a bit tedious, but okay, it's fun. It's worth it.
I have more questions, but I think we're running out of time. So congrats again. I think this is quite creative. So I don't know if Andrea.
I also would like to congratulate. I think the work is nice and the presentation was very enjoyable. I would also say it was also fun. And one little comment I have is related to the lighter. I mean, if you are in the middle of a fire, you're not willing probably to smoke a cigarette or something. And also I am afraid that it also the liquid gas over there might be even risky if you have an impact on top of there and the gas goes out. Also, if you have a fire and it is not, to me, a nice idea to have on your finger something which can explode somehow. No.
Yeah, that's completely true. We agree, but it was
just fun. Eh?
We wouldn't suppose that firefighters wear this glove with the lighter equipped. But okay, but thank you very much.
Thank you.
Okay, thank you. Bye-bye.
Thank you for your presentation. You can see all the gadgets attached to the glove. We can proceed with the presentation for Mission team. Good luck.
Thank you.
Thanks.
My team members. Okay. I'm a little sick. I'm so sorry for this. Okay, I can start. Okay. Hi, dear jurors, and hi, everyone. We are mixing, and we are my team members is Emine Mektaş, it's me, and Aliyan Kılıç, Veysel Danklan, and Yunus Emre Yavuz. We can start. The task has some recommenders. These are fire resistance, impact resistance, shock absorption, material selection, implementability. It's the feasibility, the weight and size. We try to use these recommenders. Okay, before relieving glove, it's necessary to find which one used these materials, what is used the materials. The most important point in the material selection is whether it fulfills the desired conditions. The second point, we'll look at the easy of purchase, easy supply, from the manufacturing, something common market. Considering these points, we made several material selection. Okay, first one is the Kevlar. Some groups use that, and the Kevlar is the material inspired by the structure of the spider web. And do you know the spider web is the very stronger material in the nature, and it is the 5 times stronger than steel of same weight. We can look at the picture of the Kevlar. You know that the point, next page, thanks you. It's a light and extraordinarily strong, and high strength and high cut resistance, and the low electrical conductivity, high resistance to high temperature, and the high chemical something, and the least thin filament structure that withstands very high tensile stress, and you can buy and weave different lengths of yarn, as you can see the website. You can supply.
And the other material is D3O. D3O does not obey Newton's law of viscosity. This feature makes it an interesting item. D3O gel has molecules that can flow and slide over each other without any sudden external influence. However, when a sudden and severe charge comes on, the molecules lock together and become a temporary solid, and the gel hardens. Thus, the energy caused by external influence is absorbed, but we may have issues with D3O material collection. That's why we didn't want to use this material. We decided to use rubber instead.
Material selection. Rubber has shock absorbing properties. It can be produced in different hardnesses according to contact in the mixture. In this way, it is used to different sectors. The absorbent properties of rubber make it a useful substance in automobile suspension. Rubber also dampens the vibration of industrial materials. In addition, rubber isn't conductive to electric current, and therefore it can be widely used in the areas such as insulation and isolation. In terms of conductive, it can be easily found in the markets.
Temperature control fabric. We decided to add fabrics that can change color with heat to the globe. However, we did not use the fabric on the entire globe, considering that there is a possibility of ignition in case of opposite situation. We added it as stripes for the indicator. Why we add this? Let's imagine that many people will use the globe in different work areas. Everyone's heat threshold isn't same. For this reason, next please. So will be able to see the color changes. Next. Touch screen feature. At the same time, we add fingertips to the globe, which provides ease of use with touch screen. We think that this is an important need in today's world. For example, some workers in industry work with CNC machines, but they work by removing their gloves because the use of their gloves isn't suitable for touch screens and doesn't offer comfortable movements. As a result of this, we encounter occupational accidents such as loss of hand or limb. Next, please. Compactable system. There is a tube and pump. It works like a simple pump system. As with the blood pressure monitor, the air inside the globe completely wraps the arm and provides a comfortable use. This is a mechanical system and doesn't need electricity to operate. The pump can be operated with a simple hand movement. The globe can be easily removed when the last tube cap is open and the globe is vented. In addition, since it is possible to change size with air, everyone can use a single size globe. It's a working principle
of our design pump system. In the example animation, you can see that the pump is inflated and deflated.
Okay, this is inside the wheel, this principle of the working. The air taken by the pump is filled into the inner tube. Inner tube is a shamble in Turkish, but what can we explain in English exactly? This like this, but we can use the minimalizing, like the balloon. It's the layer of our gloves. You can see the size of our layers. We less than the 10 millimeters. Rubber, Kevlar, air. Inner tube is the previous page is include. The types twice layer polyester and cotton. We use that because the maybe inner tube or the Kevlar can be harmful to skin, so we use the polyester and cotton, no cotton, because this can be burned. Last page. The design of this our glove. You can see the rubber. We prefer the piece the rubber because of the freedom to move your hand. This is some codes. Our materials. You may some piece of you can the internet. Some features like that. Thanks for listening our presentation.
Okay. Okay. I have a doubt about the impact resistance of the globe. About the fire resistance, I have no doubt. About the pressure resistance, I have no doubt. But about the big impact, I have some doubt. So if you can explain to me, please, how works this glove in front of an impact on your arm?
Okay, we mentioned at the next pages. We actually we wanted the 3O, the materials, but we can found easily. Actually, you can cover the all gloves with this material, but the rubber is not flexible to move your hands. So we want to piece your like that. You can your bones under your bones.
Okay, I think I understand. Is a non-Newtonian fluid, like a non-Newtonian fluid.
I'm sorry, I don't know in fluid that means.
No, is a kind of polymer that is fluid when no pressure is done on top, but in front of a big impact is heavy or is rigid.
Okay, let me explain your doubts for your doubts. This balloon system benefit
is a bubble system. Bubble system.
Yeah, is a bubble system. Yeah.
Air system. Bubble system.
Yes, air bubble system, and it absorbs out attacks or out shocking. So very useful.
Don't worry, Ali. The explanation of a minute was enough. Thank you.
Thanks.
Thank you very much. That's all. Okay. That's all. Thank you very much.
Any questions?
So, well, congrats for the presentation and design. To me, I really like 3 points, mixing the D3O material, the non-Newtonian fluid, and the temperature control by this kind of temperature changing color, and also the inflation system. So I have 2 questions.
Sorry.
Yeah.
I think they are not using the D3O at the end.
Yeah, that's that.
Yeah, we don't use the D3O.
Okay.
So that was going to be one of my.
We use orange rubber.
Yeah, I understood. I understood. I was just going to say so two different things. So I like the idea of the D3O, and I think you can add it kind of maybe on the surface. Maybe it can be a good idea. I don't know, to have some regions, okay? Because you said that you don't want to use it because this is too rigid, too stiff, right?
Reduce?
Well, not rigid. That for the movements, you said that you didn't use it because of that, right? So in such a case, why not putting some pieces like in different regions?
Yeah.
So you don't compromise the mobility, and then if you have a high speed impact, you can absorb more energy. So that was one of my questions. And the second one is if you have considered, so when you impose an inflation system with air pumping, instead of just inflating everything, just consider kind of metamaterial or different regions that inflate following a given pattern, so you can optimize the whole mobility plus the absorption mechanisms.
Okay. We designed for moment this design on the top of our glove. It have channels to elasticity and other part of rubbers on the on the top of the fingers. There is rubber also, so it's not problem for movement, and I hope I understand truly.
Okay, so well, that's all my comments. So congrats again. Thanks.
Thanks.
So I think that I would have I agree with Daniel, and I would have used also the non-Newtonian fluid to better absorb the shock. If I can say, I really like it that you have put the budget, which shows that this device, although perhaps being less complicated than other, is very cheap and very affordable. So this I like it. I think we are out of time, so I think we can go forward to the next presentation.
Thank you.
Thanks. Thank you. Okay.
Thank you for your presentation. I remind you that we are halfway through the presentations of this team design, so there are still five more teams to go. Sorry. So we can proceed with the presentations, and team with Ethan can present their outcomes.
So can you see us?
Yes.
Okay. Can you see the presentation?
Yes.
Perfect. Okay, so yeah, we have eaten, already done. And what was our task? Our mission was to create a lightweight, shock, impact, and fire-resistant gloves that, moreover, would be even foldable. Yep, so how did we manage to do this? So we decided to make a three-layered design. So three-layered construction for glove. It has thermal and mechanical protection. It has shock and impact protection. It has a layer for user hand comfort. This glove made of lightweight materials, and there are stiff zipper like to put on this glove easily and to put off.
So what about the outer layer? We decided to make it of meta-aramid, or how it is called, Nomex. We decided between two materials, the Kevlar and Nomex. Kevlar is also good for thermal protecting, but it's not. But the Nomex is much better, and it's used for used by firefighters, and it's easily accessible in a household. As you can see, it could be bought in Walmart, and it has perfect fire protective properties. Let's see the tests. This is the gum that is melted by fire torch, and this is the fire gum that is protected by Nomex. As you can see, it does not melt.
Okay, so our hand now is protected from thermal impact. But what about shock and impact? Actually, yes, we looked onto different anti-impact materials, but most of them have such drawbacks as they are rigid, they restrict movements, they are heavy. And then we switched to D3O. Yep, it's a revolutionary material that is soft and flexible in the normal state, but when the high pressure or force is put on it, it becomes very strong and it disperses all the force. And after that, it just becomes, returns to its normal state. Yep, and as you have seen, you can buy it, for example, in motorcycle shops. Yeah. And let's look onto the test. Yep, this guy feels great and his finger too. And what's more important, this test of different gloves, we looked onto different materials like this one, but now look what D3O is capable of. Pretty cool, no?
Okay, so and for the third layer of our glove, we decided to pick cotton because it is comfortable. It is also hypoallergenic, and we also picked that because it is low cost and it is easily accessible around the world. So it is not a problem to get this material. And another great property of the cotton is that it is eco-friendly, so it can be very easily recyclable. Yeah. Next slide. So here you can see weight and size properties of our glove. We calculated real weight of our device, so we can see it on this screen. And first live prototype. So here you can see we decided to create a real prototype of the glove. Despite we didn't have a possibility to get all the materials that you saw on the previous slides, we just used materials that were easily accessible in the house. So our prototype is equipped with a zipper that works like a Swiss watch, and it allows to easily fold the glove. And we also added Velcro to fix the device in a bag-like shape when it is transported. Next slide.
So if we talk about some simulations, yeah, the first simulation was like a temperature. So here you can see the layers with the draw and some aramid. Yeah, and here you can see that our glove can be resistant for above 1000 Celsius degree. Yeah. So what about impact testing? Here you can see the finger test. Here you have like pressure on the finger, and it's like comparable to the like 2 kilogram materials which can be thrown on this finger in our glove. So the same test we have run on the forearm part of our glove, and the results are almost the same as for fingers.
Okay, yep. So now look at our virtuoso. As I have said, our glove doesn't restrict any movement. So as you can see. Yeah, and he even couldn't play the guitar before he wore it. Yeah, and as we have said, we didn't make something that that exists only somewhere in the virtual environment. Yep, it exists right here. A real device that now, despite it made of other materials, it has great protection from impact, from temperature, and other stuff. So thank you for your attention.
Well, boys, congratulations. I think it's been the most feasible option from now. So congratulations again.
Thank you.
And you guy, I love your outfit for playing guitar. And my question, I'm kidding you. Well, my question is how easy is to have different sizes because your hand is your size hand, but people is the different sizes, small and medium and big and extra big. So how difficult it could be to have different sizes for this kind of glove? That's my question.
Okay, so there wouldn't be any problem because as there are gloves of different size in markets, the same way our glove would be the different sizes. And actually the prototype is made of market gloves, and even the kind of production version could be made of them. So
it's an all size product.
Yes.
Yeah.
Okay, include this in your presentation, please.
Okay, thank you.
Thank you.
So congratulations, I really like it. I have to say that you touched the different fields I love. So smart materials, simulation, mechanical modeling, and mechanical analysis. And I think it was a fantastic presentation and very detailed.
Great, thanks.
Details on the manufacturing, designing, and structural analysis process. So really, congratulations. And also, I have a question, and this is just going for the 10, right? So regarding the simulations you did, again, I really like that you mix all this stuff. So I just wonder, how do you simulate that? So the impact process.
So yeah, we used like SolidWorks, like the simulation stuff in SolidWorks. Yeah, so we quite new in SolidWorks, and we just have to like teach to do it. But now you can see that we apply like a temperature testing and some input testing, and we think that it's quite like not like 100% realistic, but like close to the reality results.
Yeah, and as we know, this Rio is non-linear material. Because it's soft when it's normal state and it's strong when it's under pressure. And we took the characteristic of this Rio that it has under pressure to simulate this and simplified that non-linearity.
Okay, so that's a smart simplification. And did you take into account dynamic?
Yes. We have also run simulations with a fallen object on our finger or forearm.
Okay, that's great. So
yeah, but our PC has very little resources to
run such simulations. Yes, so that's why we didn't include it.
Well, I mean, so this is too simplistic, but as a first approach, I think this is really nice. So congrats again.
Thank you. Thank you. Yeah.
So congratulations also for the project and for the playing guitar skills.
Thank you.
And one curiosity which I have is the temperature testing. So here is after how long?
Here we have for about 6 minutes.
So after 6 minutes, you start having 45 degrees inside.
But it's not inside the globe. It's on the bottom of the D3O parts. Under that, we have also a layer of cotton.
Okay, well, we will be more or less this. So good, thank you very much.
As you can see, like before on the video, the sample that was used, like it was tested for 30 minutes.
Well, but here it is a radiative transfer, and you have emissivity and so on. So in your simulation, it's 6 minutes.
Yes, yes.
So
okay, excellent.
Thank
you. Okay, thank you very much.
Thank you.
Thank you. Thank you.
Thank you for the good words. So we really appreciate that.
For your presentation, Team Mixing. We didn't, sorry. It was very nice to see the videos and actual testing of the prototype. We can proceed with the following presentation of Team Engineers. Good luck.
So we cannot hear you guys.
How about now?
Okay, now it's perfect.
Okay, awesome. We almost repeated the thing that happened to us last time. Okay, guys, I'm just getting everything ready. And here we go.
So, hello everybody, we are the engineers and we are here to present you our version of the future human augmentation. Alongside my colleagues, we are go over our prototype as in depth as possible. The world we live in is slowly starting to resemble science fiction. One of the most sought after technology, as seems in the most media, is human augmentation, whether it is to amplify one's ability or to fix the loss of one. Fortunately, technology has caught up to us pretty quickly, and now these kind of things are becoming more and more possible. Our device aims to fix both of these problems and then some. Introducing the CyberTouch, the ExoMaster machine. Our device is aimed to hobbyists, professionals, and most important, people with reduced motor skills like carpal tunnel or muscle dystrophy.
With the help of strong materials in combination with high torque motors and simple mechanisms, we can enhance human capabilities that include better grip alongside with improved thermal and impact resistance. For a better design and to ensure proper dimensions, we scan one of our friend's hand to have it as an accurate 3D reference. This process was made possible with the help of photogrammetry. Our device is comprised of tungsten wires, PTFE tubes, control box with electronics, 5 high power servos, and 3 layer sleeve through which all of our components go through. The mechanical design is based on already existing principles used in things like bikes and other widely used pulley systems like the BOA, a self-tightening pulley mechanism used in sportswear and clothing. Tungsten wires go through the tubes that connect the tip to the tip of the fingers from above and below, with the wire being wound on a pulley system on each motor. This way, one servo can control both directions necessary for extension or retraction of the fingers. In addition to the motors that are rated for 25 to 30 kilograms a centimeter and that work in a closed loop, electrodes that have been embedded in the sleeve moderate electrical signals as secondary input for the motors, this way gaining precise control for each of them. The sleeve is made out of 3 layers, as you can see here: an outer aerogel infused textile for heat protection, a middle layer made out of sorbitane for impact absorption and dissipation, and an inner fabric layer for comfort. The total thickness of the sleeve alone is less than 10 millimeters. The Teflon or PET PTFE tubes run throughout the sorbitane layer so they don't get pinched. The wires are permanently sewed to the inner layer, and length adjustments can be made by winding the wires more or less on the pulley system. Our total weight is at about 250 to 300 grams, most of the weight being comprised of the control box and servos. Last but not least, a flexible LED light is fixed upon the back of the hand for quick access to a light source.
The materials we chose to use have been heavily researched before actually starting to design the final device. We have been able to scour through datasheets and extract graphs based on previously made studies of these easily accessible materials. Sorbitane is a performant non-Newtonian material used as shock absorber in non-Newtonian materials. Stress is not proportional to strain and mechanical energy loss. We like aerogel so much that we used it once again and in this design as well. Aerogel performance made it the obvious decision as a thermal insulator and protective barrier, as seen in the GIF and graph. Aerogel is capable of reducing the thermal output by 99% compared to aluminum, making it the prime material for the most thermal barrier integration for the future. The 3 mm outer diameter PDF tubes provide excellent dry lubrication for the wires, Teflon having an inherently low friction coefficient. Tungsten wires provide mechanical actuation of the fingers while also ensuring very high tensile strength. This is important to prevent them snapping under continuous stress.
To make the Cyber Touch as versatile as possible, the motors actuate in a closed loop response based on the rotation of the pulley at every finger's move. Therefore, if you extend your finger on the side of the wire is extend, and this make the pulley spin and initiate the servo. To ensure precision, electrodes were carefully placed on the specific place alongside the forearm to monitor electrical signals. This way, based on the intensity of the current flowing, the motors can lock up, helping with grip. The gloves are also equipped with grippy vulcanized rubber, touchscreen compatible pads. Because we wanted this device to be used by many other types of people, we include a flexible LED light on the back of the hand. The light can be turned on with gestures that are recognized by the previously mentioned input methods. Additional accessories can be developed in the future to enhance the ability with such add-ons as magnetic holsters, low power e-ink displays, and additional battery compartments or motor upgrades. For the most use cases, we decide to go for a high power servo, but depending on the necessary torque, smaller motors can be installed, making the control box shorter and even smaller overload. For the purpose of this test, the control box was installed on the forearm, but if needed, it can be attached to higher up to the arm or even shoulder. When it's not in use, the control box can actuate all the servos at once, pulling the entire sleeve in and compacting it.
Thank you for watching, and this is all resources.
Okay, congratulations. A very nice and clear presentation. So good job. And just a question, and is a curiosity more than a question. Why tungsten wires?
Through research, we found out that these have the highest tensile strength of the available wires on the market, or one of the higher ones, at least that we found, at about 2,300 megapascals per millimeter square.
Yeah, that's true, but I think maybe I'm wrong, but tungsten is a very, very resistant metal, but in compression, but not in flexuring, not in tensile, because it's so brittle. That was my, yeah. So I'm not sure it's the best option. And I repeat to you the same that I said to other team. Maybe it's the most resistant material, maybe. But which is the maximum stress that can be applied to this, to your device. So maybe you don't need a tungsten wire, and you can consider other metal, much common metal and more flexible or more ductile and not so brittle as tungsten? That's my question. That's all.
No, that is a very good observation. We did spend half of the first day trying to find out the best materials that we could use, and we literally just searched for highest tensile strength out of all possible wires on the market, and this is what we found. And we didn't really think of it being too brittle. And I do know, because I did used to help with repairing old VCR recorders and other devices from the 70s that do have they do have I think it might be an alloy, but it's basically a tungsten wire that's on a pulley pulling some mechanisms in some devices like cassette tape players. It might be an alloy though. I'm not sure.
Okay, so well, congratulations. Also, really impressive work. And I really like the presentation, how you put everything, but just a small recommendation for the future. Sometimes you provided too much information in too low time. So sometimes less is more. Especially when you were indicating all the stuff regarding the gel part and the different mechanical analysis, etc. So I was really interested in that, and sometimes it was impossible to follow up, right? So my questions again. So this is super complete, and I really like the design you provide and the explanation you provide. So my question is regarding the feasibility. So again, what you're proposing looks to me that I'm not from electronics, etc. So looks quite difficult to implement. So I don't know how feasible you think it is, and some difficulties you can a priori anticipate.
Well, the glove can be made in molds and sewed with aerogel infused cords. And the electronics can explain more, my colleague Ted.
So basically what I was trying to say that we did research the availability for, I'm going to get to electronics soon enough, but feasibility obviously entails materials. So we did search all of these materials. They're easily accessible through most suppliers throughout the world. Obviously China has a lot of them. With the electronics, you said how feasible it is for it to work, basically?
Yeah.
Okay, well, we had in mind redundancy, right? So I'm in automation. These guys, Vlad is in IT, and they're medical engineers. So we always have a redundancy in mind. So the reason why we added the electrodes, first of all, precise control, is to have a redundant feature so that the arms don't actuate, like the fingers actually, don't actuate by themselves. So every single time there is an input, both devices have to have some sort of signal. So the closed loop must return a different position when you move your finger, but also you have to have some sort of current flowing from the electrodes. Feasibility, honestly, I feel that's pretty easy to program. I've done similar things with multiple inputs, not bioengineering of this kind, but with a pretty good PID controller and enough software redundancy as well, it is feasible. I feel like I actually believe that it is.
Okay, well answered. So congrats again.
So congratulations also from my side. One thing that make me a bit concerned is the fact that it relies on an electronic box, which is in a place which is a bit let's say exposed, no? In case you have a fire or something, then you cannot move anymore your hands.
The answer to the question is very simple. The handbook proposed that one of the criteria would be the entire robotic glove, or the glove that we were supposed to make, should be up to the elbow. That's why we propose that the features part of the presentation, that the box could easily be installed on the forearm, maybe in the back, but it is pretty much necessary for the implementation that we were thinking of, which is helping actuation of the fingers, whether it is for people in some sort of profession, and mostly people with motor skill problems.
Okay.
But, and yeah, because we do have the PTFE tubes that act kind of like like the tubes on a bicycle brake, they could be installed pretty much anywhere, and it's not going to make a difference. They're still going to actuate at the same weight, whether it is from here or from maybe on the backpack or something.
Okay, perfect. Thank you.
Sorry, one super quick question. Okay, can you recall me the weight?
Yeah.
We estimated 250 to 300 grams. So that would be 50 grams per piece of, for each servo motor. So that's 150. And then we estimated, the tungsten wires at 30 grams based on the 19.2 grams per centimeter squared density. And let's see, the battery should be around 50 grams as well. And then the box, which we would use probably like a duraluminum alloy, again, maybe 50. So I think I did miss something, but basically 250, 300 grams, most cases.
Okay.
So as a further comment, as Nuria was saying, whenever you try to reduce the weight, you should multiply the strength of the material times the density. Because whatever load you have, you can put more material and you will withstand more load. At the end, what is relevant for you is the product of density and strength. Okay.
Thank you very much.
Thank you.
Thank you for your presentation. It was very nice to see your result. Let's go for the last three teams to present. So now it would be time for Solid Don't Works to present the results.
Hello, everybody. Let me just share my screen. Can you see the presentation?
Yes.
Okay. Hello, everybody. We're Solid Don't Works, and we're gonna present our gloves. Hope you like it. Well, when developing our product, we actually thought as a team, what is the best way to actually present our product, and we came with the idea of actually selling the product. So we made a little infomercials. I hope you like it.
Are you a clumsy person? Does hammering a nail means hammering a finger? Cutting with a knife almost slices your finger off? Dealing with animals is a constant danger. Don't worry, here's the solution. Tripa Gloves 2000, a glove that will change your life. Constructed with a double-layered high-grade Kevlar to ensure your everyday safety, we assure you, nothing will happen to you. Do you have a gas stove? Or are you a barbecue fan? Have you already
News that is available
or are you
on
just
Prolific.
simply afraid of being grilled alive? Once more, Tripa Gloves 2000 is the answer. Its Kevlar fabric is especially designed to perform under fire and intense heat. It has a similar thought procedure as a fireman's and astronaut's equipment. If you don't believe me, believe the testimony of this fireman.
Hi, I am Bob and I'm a fireman for more than 10 years. I use Tripa Gloves 2000 in my everyday work and it has saved my life for countless times.
Does work on your backyard goes hardcore and heavy machinery is cold sometimes? Fear not that Tripa Gloves 2000 is also for you. Protect yourself when using chainsaw to take down some trees or other big plants. Any falling branches or debris won't pass the protective zones of the gloves. Just look at them, it's impenetrable! With all this protection, you must think, it must be uncomfortable. You couldn't be farther from the truth. The cotton inner layer provides impeccable comfort. We have a lightweight, compact and easily stored pair of gloves. It's the perfect product! Call now! 1-800-100-100 and get your Tripa Gloves 2000 for just the price on the screen. And if your call is one of the first 500, we will send you a support for the holy grail of gloves.
Protect yourself with Tripa Gloves.
Are you a clumsy?
Sorry.
Are you?
You're muted.
Sorry. I hope you like the information. Now we're gonna get a little bit serious about our prototype. So I'm gonna talk about the constructional solutions that we came up to assure the different to assure different protection against some of the most common hazards. So the outer layer of our prototype is made from aluminized Kevlar fabric. So it could provide some high temperature protection as well as some vibration damping, because we know from other sources that material works. So we've chosen 1.5 millimeter thickness because with the help of the other materials, we'll also have some extra thermal insulation capabilities. Next, please. For the second layer, we chose polyurethane foam, as it can provide some impact absorption and resistance to impact. When we say impact resistance, is that after every impact that it receives, it has a memory. It functions like a memory foam, so it can go back to the normal states when it was created. As well, it provides shock absorption, as we can see, as we have been, which is a common knowledge in different sports like fencing. Inside the inner layer, because is the layer that will have direct contact with the skin, we've chosen a 1 millimeter thickness cotton to provide comfort while using our prototype. To protect against some harder impacts and against the most critical zones of our hand, we've chosen polyurethane foam with PVC, which is a relatively low price thermal plastic that would help a lot with impact resistance and shock absorption.
Using GrantS LPEC software, we compared several materials. Here we can see some different thermoplastics filtered by their impact absorption, capacity, and their respective price. Next slide. We also compared the melting point of the previous materials, so the gloves can handle high temperatures. Based on these two graphics, we picked PVC because it is a material that can absorb impacts, it is cheap, and has a decent melting point. Talking about the final design, it has 160 grams. The walls of the glove have 5 to 6 millimeter thickness, so they are easy to maneuver and to use. The glove has a Velcro strap in the middle, and you can fold the glove so it fits in a small compartment.
One real question to ask is, why did we choose a design so simple? One of our main tasks was to actually have something that we could actually easily manufacture and would be really cheap. So in a world where there's so many complex designs, we really chose to simplify it. We thought about a lot of other types of solutions, but we saw some types of problems. In example, the exoskeletons or telescopic solutions, we thought that it could arrive with some problems in the future with a lot of use cycles. And ultimately we chose a low weight with good material protection, simple to manufacture, and beautiful design. In terms of price, it's relatively cheap. The highest price was the Kevlar layer.
Sum up, here is the ultimate glove you need.
Lightweight, and it protects all your arm and hand from fire heat, and thanks to the layer construction. It is capable of protecting from impacts, vibrations, and sharp objects, once again, thanks to the Kevlar layer and the polyethylene foam on the critical zones. It is comfortable thanks to the cotton inner layer, and it's super practical to store regarding the Velcro movable sleeve and the maneuverability that allows it to fold completely. It fits just like a smartphone on your pocket. So thank you for your time.
Well, congratulations for
Study is available on Prolific.
Sorry? Okay, can you hear me?
Yes, yes.
Okay. Congratulations for your presentation. Somebody told you that the telephone number doesn't work. Consider this. And when I realized you have been used the EduPack,
yes,
EduPack program, yeah.
Grant Access EduPack.
The Grant Access EduPack, yeah. I love it. I love it. So I think this option could be as easy to get as in your commercial movie. And my only question is, I have no questions. It's just like a commentary, like a comment. Do you think this could be possible to have a glove like this in laboratory for working in laboratory in practice in academic activities in an easy way, or at home as that woman who was ironing? And I must say to you that men can iron also.
It was me. It was me.
And do you think that this could be easy enough for getting in the laboratory?
I think it would be possible, but in that particular case, maybe we should choose like different materials for the specific use, maybe. But I think it's an easy solution and possible solution.
Imagine when we are using something in an academic problem, we're not reaching like critical temperatures, or often like very high. Besides, this glove can withstand really high temperatures, like 700 degrees. So it won't be a problem in the general world functioning. But for a specific kind, the majority of applications, this glove works just fine.
I agree with you. In heat treatments, you can be working in temperatures more than 1000 degrees. I did it during my research. So this is the only option I need. My usual glove was not enough for me, and I burned my hands many years ago for that reason. That was my question was related to this. But okay, that's all. Thank you very much, and congratulations again. I love it. I love your presentation.
Thank you.
Thank you.
Okay, so well, congratulations for the presentation and the design. And actually have like kind of contradictory feelings. On the one hand, this is like from the scientific part. So I think this is quite simple, okay, but this is true that this is your purpose, right? And on the other hand, so the marketing stuff is extremely good. So I really like, and I feel that I think this is Mario, the one who risking your life, right? Cutting and doing the whole stuff in the video. So for me, now let's give you a shot. So try to tell me in half a minute, 1 minute, more on the specific technical, and let's say more from a technical point of view, 3-4 reasons why your design is better than others. So okay. I got the marketing bit, but now from a technical point of view, try to sell it to me. Right?
I think one key point in terms of as the competition asked, the fire resistant part, I think the aluminized Kevlar fabric really makes a difference. That should be one point. And maneuverability is our design really is really good on that key point. That's important.
It was one of the most feasible solutions that we have come up in this afternoon.
And
sorry,
we truly believe that the PVC plus polyurethane foam is a really good solution for absorption. And it's a really easy one too, and quite easy to manufacture.
Okay, and just like last super good question, if you need to change something, or if you can change something in your design, which is the change that you will propose?
That's a good question.
That is the impact from the technical aspect.
Regarding the impact aspect?
Well, technical aspect.
Okay, I've actually tried to kind of predict the impact behavior, but those kinds of analysis of nonlinear dynamics are difficult to do regarding the normal software that we have, that not everyone has a software capable of running those types of simulations in this lack of time. So it would be a very difficult study to prepare in such small time conditions. However, if we could improve the impact aspect of this glove, of course we could extend the protection layer to all our arm or something. Of course, we would have to discard some of the mobility, or we can change the material to something more resistant, like PEEK, or like it was said before in this afternoon, like some non-Newtonian fluid or something like that.
Okay, so thank you very much, and congrats again for the nice presentation and the nice movie.
Thank you very much, and I would like to congratulate for the commercial. It was a lot of fun, and I think the solution is simple but effective. What I missed a bit is a bit of a cost estimation, but I understand that it is a cost which is totally affordable. No?
Can you repeat the question? We weren't able to understand.
What I missed a bit is the cost estimation. How much would it cost?
Oh, we ran some numbers. It would be relatively cheap. The PVC is real cheap. The highest cost would be the Kevlar material.
The problem here would be the quantities of the materials, right? The problem here is not how much the materials are, because the materials used are relatively cheap. PVC is cheap. The most expensive material used is Kevlar, which is like 5 euros meter square or something like that. So 25 euros meter square, sorry. And the problem here would be the manufacturing prices. But if you could make in a large scale, it would be a relatively low price for the kind of protection that we offer.
Okay, thank you very much.
Thank you for your presentation. Let's go to the next to last team to present, Spigoli Vivi.
Hi. Hello. Can you see us? You have to share the screen. Yes. PowerPoint presentation.
Yes.
Okay. Are you able to see our presentation?
Yes.
Okay, thank you.
Thank you.
Hello, everybody. We are Team Spigoli Vivi from the University of Naples Federico II, and the name for today of our prototype is Fire Glove. You will understand the meaning later. First of all, as usual, we started from the customer needs. We analyzed them in deep, and then we moved to an initial phase of brainstorming. we thought of different types of invincible gloves, for example, Donnarumma's one, or also the ones of the firefighters. Then we moving to the name of our prototype, it is fire. These names comes because our gloves are resistant to flames and impact, but our gloves are also retractable and effective. This is our prototype, and as you can see, in the lower part of the slide, here are the overall dimensions and also the weight of our prototype for a pair. Regarding the material used for our prototype, we made it of different layers. Each layer has a specific function to satisfy a different customer requirement. In particular, we paid a lot of attention in the positioning of the layers, because if you use the wrong positioning, the globe will change its features. In total, we reached the thickness of 8 millimeters. But now let's move to the layer in the specific.
Okay, so let's take a closer look to the single layer. The outer layer is called outer shell, and is composed of a fabric of multi-filament technology of Kevlar and Nomex in order to achieve exceptional strength, flexibility, comfort, and exceptional thermal properties. And then we have a thermal layer that is under the first layer, that is a key layer to insulate the user from the fire, from the outer things that could harm the user. And it's very important. And it's composed by a bitting of Nomex E89 and a fabric of Nomex. Then we have the impact resistant and shock absorption layer. This layer is composed by a viscoelastic foam with memory effect. We decided to use this material because we searched on the internet, and this material had exceptional properties regarding the impact absorption. It is also impact compliant, and it is able to dissipate the energy during impact, protecting the body of the user. But it is also has a lot of interesting features like environmental compatibility, temperature stability that is very important in a glove that has to resist to fire, and then last but not least, comfort. And then we search for tests on this material. As you can see on the graph on the left, it is tested to impact a traditional elastomer used in padding for protecting the user. On the right, you can see the same test done with this viscoelastic foam that is, the curve is a lot lower. So it means that the transmitted energy during this test is a lot lower. We decided to position the layer, as you've seen before, in a strategic position. So on the arm, where the user could be beaten from something, and on the palm of the hands, and also on the back of the hands, in some padding. Okay, so let's talk about comfort. Comfort for sure is very important for a glove, and this is the reason why we add in the inner layer a layer made of cotton. That is for sure has a good feeling on our skin. All materials that we use are flexible, and this is very important to ensure for the customer the normal movements of hand. Also, is also very important the breathability for gloves we thought, and this is the reason why all the materials that we use ensure a good breathability, and the only one layer that probably has some issue in this case is the impact attenuator layer, and this is the reason why we choose to have a non-ecom geometry to solve this problem. Okay, the gloves is also to be retractable, and this is, as I said a few seconds ago, all the materials that we use are flexible, and also the impact attenuator layer is very flexible, as you can see in the photo in the slide. However, we divide this impact attenuator layer in different pieces, as you can see in the first photo, and this make our gloves able to
to assume the shape that you can see in the second part of the first photo. And in the second photo, you can see in a better way how the system works. Okay, it's also important. We thought that feasibility is also very important, and all the materials that we use are easily available in the market. In fact, they are yet used in the common market, and all the production process that we need are largely tested. In fact, they are yet used. So to sum up, our product is fire resistant, is thermal insulator, is impact resistant, the shock absorption of our gloves is very good, the feasibility is absolutely good. The weight is not too much. In fact, one glove, the weight of one glove is only a little bit more of 200 grams, and is retractable. And we as a team, we are very, very happy because we respect all the tasks using a very, very simple geometry, very simple material, and this is something that makes us sure that our prototype is able to work and is able to be produced without any problem. So thank you.
If you have any questions, we are here to answer you.
Okay. First of all, congratulations, because the presentation and the project was clear and was, in my opinion, a good job. And my only question is related to the glove is retractable. Retractable gloves are, in my opinion, a good option for a thin arm, but when the thin is so wide, so in my case, I have a wide arm, then retractable elements are not good enough because they stop depending on the size of the arm. So can you solve this? How can you solve this?
Okay. Okay. We divided the layer of the impact actuator in different parts to make us able to have some small parts without the impact actuator parts, and this make the gloves able to be foldable, because without the impact actuator layer, it's easier to have the foldability of the gloves, but the spaces that we need aren't very, very large, because sorry,
the microphone.
I think it doesn't work. Maybe a flexible element could be a good option.
The padding are really soft material. It can be
soft. So is it flexible?
Because as we saw in the slides. Okay, I will show you.
It's not stiff. It's not stiff. It's not
stiff. Absolutely not.
Okay.
It's flexible. Just a moment.
Just a moment.
As you can see, our padding is made of this material that you can easily fold it.
I didn't understood the draw, and I thought it was the aspect when it's retractable. After all the elements are folded. Okay, I understood.
They fold.
Oh yeah. Now I can see. Okay, yeah.
Maybe it was too fast, so it was difficult to follow. But we draw this simple scheme only to try to explain the concept, because we didn't model, because it was a soft structure, so it was difficult.
The disc, the cylinder is flexible.
Yes, because they are of this material that it can be easily. It's like sponge. It's foam.
Like a neoprene. Yeah. Okay.
Exactly. That is.
Thank you very much.
Thanks to you.
Thank you to you.
Okay, so thank you very much for the presentation and congratulations for both the award design and presentation you did. So as Nuria said, it has been super clear, and I think you put all the elements there, right? I have a question, it's like technical aspect. I would like to know how or which features or if you can comment something on the choice of the material for the resistant impact. So because you mentioned foams or other viscoelastic materials, so I would like to know how you have chosen this and which are the different characteristics or points you have taken into account for this choice.
Okay. Okay. So we chose this elastoplastic material because we initially searched for padding for sports equipment.
Elastoplastic or viscoelastic? Because if this is elastoplastic.
Sorry, viscoelastic material. Sorry. So we look for the materials used in sports padding. Then we saw different tests on these materials, and we decided to choose the one who had the greatest scores. So we searched for that material, that that item that scored the most point, and we discovered that the material used in that padding was this viscoplastic material. The company that produces is called Sestec company. So we didn't want to say the name of the company because we decided to stay to use the generic name of the material, but so we decided this material for this reason, because it had the most high scores in impact tests, as you can see in the presentation. The curve that describes the dissipation of energy is really low.
And also because they sell their material in meters, so it's easy to obtain and also to make our product with what they can sell you. They don't only sell finite products, but also raw materials. Okay. So it can be useful for our scope of creating a group.
Okay, so basically somehow, so it was an interesting point that instead of doing something like that, like a peak in the force, you assert the same energy level by keeping this constant, right? So in the end, okay. I mean, so this is something I think is happening with, but I didn't see properly the picture.
You can show the presentation again.
For helmet design, for example, to reduce the force peak, you see. So basically, you are absorbing more or less the same. Well, we cannot say from here.
Okay. Because you say because the force is an higher peak, but is more narrow curve.
Exactly. So I think this is an interesting point, because I know some startups companies for helmets that are using this concept. So I like this.
Okay. Because it has a really slope, really small slope, so it is absorbed more gradually. It has not an impulse in the force. Okay. That is the problem when you have a contact with something.
Mm-hmm. Okay, thank you very much, and congrats again.
Thank you.
Congratulations.
Thank you.
I think the work was nice, the presentation was clear. I also found a lot of quantitative details. You don't mention much about the price. How much would it cost?
Okay. So we didn't work a lot on the price only because it wasn't a task, but we are sure that the cost is more or less elevate, because all the materials that we used are commonly used in firefighter equipment, yes, or in sports equipment. So it could be in line with the cost of that kind of equipment. And also the process are processes that in the textile industry are commonly used. So probably we only need the textile production, and the layer for the impact attenuator is made of a very flexible material, and is easy to be sewn, shaped in any form, because at the base of the production is in liquid form, in this liquid phase. So it can be stamped in the shape that we need, and it's not very difficult to obtain that. So probably the price is the price of a common gloves, obviously made for protection of people, that is yet on market.
Okay, very good. Thank you very much.
Thank you.
Thank you. Super good question. The weight that I forgot it. Weight.
We are here.
Yes, so the weight of the total weight.
Okay. The weight is about 225 grams.
Okay.
For glove.
For each glove.
Yeah.
Okay, thank you.
That is in line with firefighter gloves. We checked on internet, so.
Thanks.
Thank you. You're welcome.
Thank you.
Now it's time to move for the last presentation of the team design category of IBEC final. Let's move on with the results and outcomes of Team Visionary. Good luck.
Okay. Can you hear me now? 1, 2, 3 test. Okay, I think you can hear me, right? Can somebody confirm, please?
Yes.
Okay, thank you very much. We are Team Visionary, and first off, we were listening to presentation for 2 hours now, so please everybody stand up, take a deep breath, and sit back down to get some of that concentration back, if you will. Okay, I will wait a couple of seconds. So I think everybody's ready now. So we are Team Visionary, and today we're gonna present you our idea of the glove. It's named Air Force One. We are Jean, Anya, and Dario, and Druk, and let's go into the presentation. So first off, I will tell you about something about existing solutions, and then what's our solution, what's the materials, inspiration, technology, protection, and portability. So let's start with the existing solutions, which do the tasks we were given. So you have normal construction gloves, then fireman gloves, which protect you against fire, and then medieval gloves, which are good for impact protection and sword attacks and stuff like that. And our Air Force One glove combines all these features into one glove. So let me tell you what we were inspired by. So we were inspired by air and air bubbles, and you will soon see why. So the materials we've used, first one is cotton. Cotton is comfortable on the skin, and that's pretty much why we used it for the bottom layer. Then we have Captain. This is foil, which is also used in aerospace applications. It's a very fancy foil. It has very good like heat resistance, and it works very good for that. Then we have Kevlar reinforced rubber. So that's the interesting part we didn't hear today yet. So if you fill up Kevlar reinforced rubber with 10 bars of air pressure, it's hard as a rock. If you never felt a road bike tire, it's hard as a rock. Believe me. Then we have Kevlar Fabric, which is very good for slash attacks with swords. It's also very heat protect resistant. Yeah, it doesn't burn that easily. And it's also used in bulletproof vests, so you could say it has unlimited power.
Okay, so we created two different arrangements. First one on the picture is designed for less movable parts of the arm and is more force resistant. It consists of thin cotton glove, inflatable rubber skeleton, capped bubble wrap, and a layer of Kevlar fabric. You can see that the thickness does not exceed 10 millimeters. This arrangement is used for these parts marked yellow. The second arrangement is without rubber, which is replaced with Kapton tubes with lower pressure that ensures more flexibility and is used in the yellow regions.
And now, how is this implemented in our glove? Firstly, we start with a cotton glove on which the already mentioned high pressure rubber is put. On the parts of the glove which ensured great rigidity and are protected against bigger dangers that can hit us. Then on top of this, Kevlar bubble wrap or tubes are put as a heat-resistant material and good heat isolator. On top of that, we put a Kevlar sheet, which additionally protects us against any cuts and other things. And lastly, we put few metal rings that finalize our product. And why do we even have metal rings? Our glove can open up to the wrist, so we can easily put our hand into it. We firstly start with the deflated device, put our hand into it, and buckle up our rings. Once all the rubber is pressurized, the geometries inside the rubber, as showed before, simply force the rubber on the outside to form the circle and tighten up all the rings.
So here an image of how the inside of the glove moves. We can see how joints spread out with the hand movement. The outside of the glove is movable just like a normal glove. So our glove is portable. You can fit it in a small box, pump it, and then it stays firmly on the hand and protects you against outside forces. So thank you, that's all.
So now the questions, please.
Well, first of all, congratulations. I think you have developed a good job and a good proposal. I think it's feasible, and why not? This option could be real. And my only question is can you show me please the picture with the Kevlar fabric?
Yeah, sure.
It was the first of the number 3. Or... okay, this one.
This one?
Okay, no, the previous one.
This
one. This one is Kevlar fabric. Okay, are you sure this is Kevlar fabric?
It's possible. It's half.
Oh yeah. Oh yeah.
It's only for. Yeah, I'm sorry for interrupting, but it's
a
for demonstration.
50-50 Kevlar and carbon fiber.
Yeah.
Kevlar is yellow.
Yeah. We didn't intend to use 50-50 as we.
And the next picture, please show me the next slide.
Yeah.
In the next slide, okay, no, yeah, in the next slide, in the
bottom layer,
Kevlar, the bottom, that's not Kevlar. That's glass fiber. That's glass fiber and carbon fiber.
That's for presentation purposes.
But
I would like to add that inventor doesn't have a library for Kevlar, only for carbon fiber.
But this is not Kevlar. This is glass fiber and carbon fiber. There are no Kevlar in this in this picture. That's my comment. Yeah, it's just a comment. When you are doing a presentation, you must be reliable with the elements you are showing. That's all. So instead of this picture, you can choose a yellow one, or painting a yellow one with computer is easy to do, but this is not Kevlar. That is the only thing. Is just a comment. That's all. Thank you very much.
Thank you, Tutu.
Okay, thank you very much for the presentation and congratulations for the work. Actually, something I really like is that you are starting like a scientific conference, let's say, introducing a state-of-the-art kind of existing solutions and motivating the whole thing from there. So this is something I really appreciate it. And well, so now regarding the question, so my first question is regarding the bubble foil. So this is a regular one. It's like the bubbles we use for presents, etc., or you are thinking about something more?
No, that bubble wrap is made from Kapton foil, so it's heat resistant. And why it's bubble wrap? Because it has air in it for insulation. Okay. As we know, as a very good insulator.
Okay,
Kapton bubble wrap is not realized currently on the market in big quantities. Usually it's the normal plastics are used. We just think out of the box and thought that this should be implemented in such case.
And okay, so in such a case, you consider that if we have a kind of impact, so this is not going to explode?
No, it should not. Like that, there defects. But like if we watch Tour de France, like not many tires explode.
Okay. Also, you had so you said about heat resistant, but I think you said in the very end about that this is not high conductivity, right? So you can develop a little bit more on. So I agree with the heat resistance, but okay, so it can not melting, etc., not destroying the material, but maybe the conduction is high and you feel it.
I don't really know what you are talking, because I didn't understood the question fully, but we try to implement air layer between the outside layers, inside layer, with the heat resistant materials that are really light and don't represent any additional weight on the arm, and at the same time are 300 degrees plus resistant.
Okay, I get your point. Okay, so congrats again. That's all from my side.
Thank you.
Congratulations also from my side. I think it is an interesting project. I think it is enough simple to be feasible. It is a bit more complex than others that we have seen before, but it is working well and reasonably feasible. In terms of feasibility, did you check how much it would cost to manufacture it?
Compared to other gloves, I think we compare to the simple gloves. Like it's sheet of Kevlar, sheet of cotton. Like Kapton foil also doesn't cost much. Like it's not some rare material, and rubber is also very common. So those are all relatively cheap materials.
And how much is the weight?
Like I calculated the weight, and realistically we come to 400 grams, because the sheet of Kevlar to cover one hand, it's 200 grams. I don't know what other teams calculated. It seemed to me a bit strange, but I calculated that to cover one arm in Kevlar, it's 200 grams. realistically, our glove would come in at about 400, 500.
Okay, thank you very much.
Yeah, thank you.
So thank you guys for your presentations. You can now open your mics because you have finished the team design category of the EUROVEC Final 2021. Congrats. I hope you had a lot of fun. I hope you stressed a little bit during the past days. I hope that you are satisfied with your results. That's the most important part because you did amazing things. So thank you for your effort, your enthusiasm, and your innovation. I would like to take a moment to thank the jury of today's team design, Nuria, Daniel, and Andrea, for being here with us, supporting the competition and providing that point of view of professional life on this competition. For the participants, this is a reminder that the competition is over, but not the event, because tomorrow we have one of the most exciting days. It's the closing day of the competition. It will start at 9:30 a.m. Central European Summer Time with a career fair. And that way you will get the chance to meet our partners and know what they're doing in industry. They will get a chance to talk to you, and it would be very interesting for finishing a competition because you did amazingly and they want to meet you. It will be followed by an hour at 11:30 for some interviews in case that you are interested in meeting them one-to-one and speaking to them directly. It would be possible for you. Then you will have a break for lunch, and at 4 p.m. we will be having the award ceremony. In that ceremony, you will get to know the winners of the European Best Engineering Competition, so I'm sure you do not want to miss it. After the award ceremony, we will be closing with a chill networking session from 6 p.m. until 7 p.m., in which you will get a chance to talk to everyone involved, organizers, other participants, partners, in a more flexible and friendly environment. Knowing the winners, knowing everything, you can breathe now and you can relax for an hour. For the winners of the competition, you will have the chance, your own table on the networking, to be there at the beginning of the session so that you can show other fellow participants, representatives of companies, or anyone attending the networking what you did and why did you win. That can be a very interesting experience, so I encourage you all to attend. That's still part of the event, and after tomorrow, you could know that you have made it. So thank you again for coming. Now the jury will go to discuss the results, and I hope to see you all tomorrow unveiling their results. Thank you.